Identifying potentially hazardous electrical situations is very important. When encountering older homes with knob and tube wiring, it's crucial to understand that these systems typically lack a dedicated ground circuit. The presence of 3 prong receptacles in such a setting should immediately raise suspicion, as they require a proper ground connection for safe operation. Homeowners sometimes attempt to address grounding issues by improperly connecting the ground terminal of a receptacle to the neutral terminal. This creates a dangerous situation because it bypasses the necessary isolation between the neutral and ground conductors. This improper grounding can lead to several problems. Firstly, it can create a path for stray current to flow on the ground wire, which can energize metal parts of appliances or equipment. Secondly, it can interfere with the proper operation of ground fault circuit interrupters, or GFCIs, which are designed to protect against electrical shocks. Thirdly, it can create a false sense of security, as the electrical system may appear to be properly grounded when it is not. It is important to note that plug testers may not always detect this improper grounding. These testers typically check for basic wiring errors such as reverse polarity or an open ground, but they may not be able to identify a situation where the ground and neutral are improperly connected. Therefore, visual inspection is essential when evaluating electrical systems in older homes. When inspecting receptacles, look for any signs of tampering or modifications, such as wires connected to the ground terminal that are also connected to the neutral terminal. If you encounter this situation, it is crucial to correct it immediately. The proper way to address grounding issues in older homes is to install a new, properly grounded circuit. This may involve running a new ground wire from the receptacle to the service panel or installing a ground rod and connecting it to the service panel. It is also important to ensure that the neutral and ground conductors are properly separated at the service panel. The neutral conductor should be connected to the neutral bus and the ground conductor should be connected to the ground bus. These 2 buses should only be connected at the service entrance. If you are unsure about the electrical wiring in your home, it is always best to consult with a qualified electrician. A licensed electrician can properly evaluate your electrical system and identify any potential safety hazards. They can also make recommendations for upgrades or repairs that will improve the safety and reliability of your electrical system. Furthermore, consider installing GFCIs to provide added protection against electrical shocks. GFCIs are designed to detect ground faults, which are electrical leaks that occur when current flows through an unintended path, such as a person's body. When a GFCI detects a ground fault, it quickly trips the circuit, cutting off the flow of electricity and preventing a potentially fatal shock. GFCIs are particularly important in areas where water is present, such as bathrooms, kitchens, and outdoor locations. They should be installed on all circuits that serve these areas. Several key recommendations to consider. Firstly, always visually inspect electrical systems for potential safety issues. Secondly, never connect the ground terminal of a receptacle to the neutral terminal. Thirdly, if you're unsure about the electrical wiring in your home, consult with a qualified electrician. Fourthly, consider installing GFCIs to provide added protection against electrical shocks. Here is some more context on general electrical safety and some additional points to consider. Electrical safety is paramount in any building, whether it's a new construction or an older home. Understanding the fundamentals of grounding, wiring, and protection devices like GFCIs is essential for preventing electrical hazards. In electrical systems, grounding refers to creating a low impedance path for fault current to return to the source. This path helps to quickly trip a circuit breaker or fuse, cutting off the power and preventing an electrical shock or fire. A proper grounding system typically consists of a grounding electrode, such as a ground rod or metal water pipe, connected to the service panel. From the service panel, a ground wire runs to each receptacle and electrical device. The ground wire provides a path for fault current to flow back to the source, tripping the breaker and preventing a dangerous voltage from building up on the metal parts of appliances or equipment. Neutral is the return path for normal load current in an electrical circuit. In a typical 120-volt circuit, the hot wire carries the current to the load and the neutral wire carries the current back to the source. The neutral wire is typically connected to the ground at the service panel, but it should otherwise be isolated from the ground throughout the electrical system. Maintaining this separation is crucial for preventing ground loops and ensuring the proper operation of GFCIs. GFCIs are life-saving devices that protect against electrical shock. They work by monitoring the current flowing in the hot and neutral wires of a circuit. If there is a difference of more than a few milliamperes between the two currents, it indicates that some of the current is leaking to ground. This could happen if someone touches a live wire or if there is a fault in an appliance. When a GFCI detects a ground fault, it quickly trips the circuit, cutting off the power and preventing a potentially fatal shock. GFCIs are required by code in areas where water is present, such as bathrooms, kitchens, and outdoor locations. They are also recommended for use in other areas where electrical shock hazards may exist. When working with electrical systems, it is essential to follow all safety precautions. Firstly, always turn off the power to the circuit before working on any electrical components. Secondly, use insulated tools to prevent electrical shock. Thirdly, never work on electrical systems when you are wet or standing in water. Fourthly, if you are unsure about any aspect of electrical work, consult with a qualified electrician. Here's a deeper dive into why the neutral and ground wires must be separated, except at the main service panel. The reason for this separation is to prevent current from flowing on the ground wire under normal operating conditions. The ground wire is intended to be a safety conductor, only carrying current during a fault. If the neutral and ground wires are connected at multiple points, some of the normal load current will flow through the ground wire, creating several potential problems. Firstly, it can create a ground loop, which is a condition where multiple ground paths exist between 2 points. This can cause unwanted current to flow in the ground wires, leading to noise and interference in electronic equipment. Secondly, it can interfere with the proper operation of GFCIs. GFCIs rely on the fact that the current in the hot and neutral wires should be equal under normal conditions. If some of the neutral current is flowing through the ground wire, the GFCI may not be able to detect a ground fault. Thirdly, it can create a shock hazard. If the ground wire is carrying current, anyone who touches a grounded metal object could receive an electrical shock. To prevent these problems, the neutral and ground wires should only be connected at one point, which is typically at the main service panel. This ensures that the ground wire only carries current during a fault and that the neutral wire carries the normal load current. It is also important to ensure that the ground wire is properly sized to handle the potential fault current. The size of the ground wire is typically determined by the size of the circuit breaker or fuse protecting the circuit. The National Electrical Code, or NEC, provides guidelines for sizing ground wires. For example, according to NEC Table 250.122, a 20 amp circuit requires a 12 American wire gauge, or AUG, ground wire. A 30 amp circuit requires a 10 AWG ground wire, and so on. Proper grounding and wiring practices are essential for ensuring the safety and reliability of electrical systems. By following these practices, you can help to prevent electrical shocks, fires, and other hazards. Remember, if you are not comfortable or knowledgeable about electrical work, always consult a qualified electrician. Now let's expand on the importance of visual inspections and what to look for. Visual inspections are a critical component of electrical safety, especially in older homes. Wall plug testers can provide a quick check for basic wiring errors. They cannot detect all potential hazards. A thorough visual inspection can reveal problems that a plug tester might miss, such as improper grounding, damaged wiring, and overloaded circuits. When performing a visual inspection, start at the service panel. Look for any signs of damage, such as rust, corrosion, or burnt wires. Make sure that all of the circuit breakers are properly labeled and that they are sized correctly for the circuits they protect. Check the grounding system to ensure that it is properly installed and that the ground wires are securely connected. Next, inspect each receptacle and switch in the home. Look for any signs of damage, such as cracks, chips, or loose connections. Make sure that the receptacles are securely mounted and that the cover plates are in place. Check the wiring to ensure that it is properly connected and that there are no exposed wires. Pay close attention to any three-prong receptacles that are installed in areas that are not properly grounded. These receptacles may have been improperly grounded by connecting the ground terminal to the neutral terminal, which is a dangerous practice. If you find any evidence of improper grounding, consult with a qualified electrician to have the problem corrected. Also, look for any signs of overloaded circuits. Overloaded circuits can cause the wires to overheat, which can lead to a fire. Signs of an overloaded circuit include flickering lights, tripping circuit breakers, and warm receptacles or switches. If you suspect that a circuit is overloaded, try to reduce the load in the circuit by unplugging some of the appliances or devices that are connected to it. If the problem persists, consult with a qualified electrician to have the circuit upgraded. In addition to inspecting the electrical system, it is also important to inspect the electrical appliances and devices in the home. Look for any signs of damage such as frayed cords, cracked housings, or loose connections. Make sure that all of the appliances are properly grounded and that they are used according to the manufacturer's instructions. Never use an appliance that is damaged or that has a frayed cord. These appliances can pose a serious electrical shock hazard. Regular visual inspections are an important part of maintaining a safe electrical system. By performing these inspections, you can identify potential hazards and take steps to correct them before they cause a problem. Remember, if you are not comfortable performing visual inspections yourself, consult with a qualified electrician to have them done for you. They can also provide recommendations for upgrades or repairs that will improve the safety and reliability of your electrical system. Let's delve deeper into the specifics of knob and tube wiring and the challenges it presents. Knob and tube, or K&T, wiring is an older type of electrical wiring that was commonly used in homes built before the 1940s. It consists of single insulated wires that are supported by porcelain knobs and tubes. The knobs are used to support the wires along walls and ceilings, and the tubes are used to protect the wires as they pass through walls and floors. One of the main challenges with K&T wiring is that it typically lacks a ground wire. This means that there is no path for fault current to flow back to the source, which can increase the risk of electrical shock or fire. In addition, the insulation on K&T wiring can become brittle and cracked over time, which can expose the bare wires. This can create a shock hazard and increase the risk of fire. Another challenge with K&T wiring is that it is not rated for the same ampacity as modern wiring. Ampacity refers to the amount of current that a wire can safely carry. K&T wiring is typically rated for a lower ampacity than modern wiring, which means that it cannot handle the same amount of load. This can lead to overloaded circuits, which can cause the wires to overheat and potentially start a fire. Because of these challenges, it is generally recommended to replace K&T wiring with modern wiring. However, replacing K&T wiring can be a costly and time-consuming process. In some cases, it may be possible to leave the K&T wiring in place and simply add a ground wire to the existing circuits. This can be done by running a new ground wire from each receptacle to the service panel. However, this is not always possible, and it may not be the safest option. If you have K&T wiring in your home, it is important to have it inspected by a qualified electrician. They can assess the condition of the wiring and make recommendations for upgrades or repairs. They can also help you to determine whether it is necessary to replace the K&T wiring with modern wiring. If you decide to replace the K&T wiring, it is important to hire a qualified electrician to do the work. Replacing K&T wiring can be a complex and dangerous task, and it should only be done by someone who is properly trained and experienced. When replacing K&T wiring, it is important to use modern wiring that is rated for the appropriate ampacity. It is also important to install ground wire in each circuit. This will help to protect against electrical shock and fire. In addition to replacing the K&T wiring, it is also a good idea to install GFCIs in areas where water is present. GFCIs can provide added protection against electrical shock, especially in older homes that may not have a ground wire. Remember that electrical safety is a top priority. Whether you're dealing with K and T wiring or modern wiring, always follow safety precautions and consult with a qualified electrician when needed. Let's explore the purpose and function of a ground fault circuit interrupter, the GFCI. A GFCI is a safety device that protects people from electrical shock. It works by monitoring the current flowing in the hot and neutral wires of a circuit. If there is a difference of more than a few milliamperes between the two currents, it indicates that some of the current is leaking to ground. This could happen if someone touches a live wire or if there is a fault in an appliance. When a GFCI detects a ground fault, it quickly trips the circuit, cutting off the power and preventing a potentially fatal shock. GFCIs are required by code in areas where water is present, such as bathrooms, kitchens, and outdoor locations. They are also recommended for use in other areas where electrical shock hazards may exist, such as garages, basements, and laundry rooms. GFCIs are available in several different types. Receptacle GFCIs are designed to replace standard electrical receptacles. They have a built-in GFCI that protects the receptacle and any other receptacles that are wired downstream from it. Circuit breaker GFCIs are designed to replace standard circuit breakers in the service panel. They protect the entire circuit from ground faults. Portable GFCIs are designed to be plugged into a standard electrical receptacle. They provide GFCI protection for any appliances or devices that are plugged into them. When installing a GFCI, it is important to follow the manufacturer's instructions carefully. It is also important to test the GFCI regularly to ensure that it is working properly. To test a GFCI, press the test button on the device. This should trip the GFCI and cut off the power to the circuit. If the GFCI does not trip, it is not working properly and should be replaced. GFCIs are an important safety device that can help to protect people from electrical shock. By installing GFCIs in your home, you can significantly reduce the risk of electrical injury. Let's clarify common misconceptions about grounding and neutral connections. There are several common misconceptions about grounding and neutral connections in electrical systems. One misconception is that the ground wire is the same as the neutral wire. While both wires are connected to the same point at the service panel, they serve different purposes. The neutral wire carries the normal load current, while the ground wire is intended to be a safety conductor, only carrying current during a fault. Another misconception is that it is safe to connect the ground wire to the neutral wire at multiple points in the electrical system. This is a dangerous practice that can create ground loops and interfere with the proper operation of GFCIs. The ground wire and neutral wire should only be connected at one point, which is typically at the service panel. Another misconception is that GFCIs protect against all types of electrical shock. GFCIs only protect against ground faults, which are electrical leaks that can occur when current flows through an unintended path. They do not protect against shock from touching a live wire. Another misconception is that it is okay to use a 3-prong adapter to plug a 3-prong appliance into a 2-prong receptacle. This is a dangerous practice that can eliminate the grounding protection of the appliance. If you need to plug a 3-prong appliance into a 2-prong receptacle, you should have a qualified electrician install a properly grounded 3-prong receptacle. Understanding the differences between grounding and neutral connections is essential for electrical safety. By avoiding these common misconceptions, you can help to prevent electrical shocks, fires, and other hazards. Let's discuss the relevant sections of the National Electrical Code, or NEC, regarding grounding and wiring. The NEC is a widely adopted code that provides standards for safe electrical installations. It contains numerous sections that address grounding and wiring requirements. Some of the key sections include Article 250, which covers grounding and bonding. This article provides requirements for grounding electrodes, grounding conductors, and equipment grounding. It also addresses the separation of neutral and ground conductors. Article 300 covers wiring methods. This article provides requirements for the types of wiring that can be used in different applications, as well as the installation methods. It also addresses the protection of wiring from physical damage. Article 310 covers conductors for general wiring. This article provides requirements for the size and ampacity of conductors used in electrical systems. It also addresses the insulation requirements for conductors. Article 406 covers receptacles, cord connectors, and attachment plugs or cord sets. This article provides requirements for the installation of receptacles, including the grounding requirement. It also addresses the use of GFCI protection for receptacles in certain locations. NEC Section 250.24 covers grounding service supplied alternating current, or AC systems. This section requires that the neutral conductor of a service-supplied AC system be grounded. The grounding connection must be made at the service entrance. NEC Section 250.130 covers equipment grounding conductor connections. This section provides requirements for connecting equipment grounding conductors to the grounding electrode system. It also addresses the use of grounding jumpers. NEC Section 310.15 covers ampacity of conductors. This section provides tables that list the ampacity of different sizes of conductors based on their insulation type and temperature rating. The NEC is a complex and comprehensive code. It is essential for electricians and other electrical professionals to be familiar with NEC requirements for grounding and wiring. By following the NEC, you can help to ensure that electrical installations are safe and reliable. Let's recap the importance of consulting with a qualified electrician. Electrical work can be dangerous and should only be performed by someone who is properly trained and experienced. A qualified electrician has the knowledge, skills, and tools to safely and correctly install, repair, and maintain electrical systems. Consulting with a qualified electrician is especially important when dealing with older homes that have K&T wiring. K&T wiring can be complex and challenging to work with, and it may require special techniques and equipment. A qualified electrician can assess the condition of the K&T wiring and make recommendations for upgrades or repairs. They can also help you to determine whether it is necessary to replace the K&T wiring with modern wiring. Even if you are comfortable doing some electrical work yourself, it is always a good idea to consult with a qualified electrician before starting any major project. They can provide guidance and advice to help you ensure that the project is done safely and correctly. When choosing an electrician, it is important to select someone who is licensed and insured. A licensed electrician has met the requirements set by the state or local government to perform electrical work. Insurance protects you from liability if something goes wrong during the electrical work. It is also a good idea to check the electrician's references and read online reviews before hiring them. This could help you to get a sense of the quality of work and customer service. Consulting with a qualified electrician is an investment in your safety and the safety of your home. By hiring a qualified electrician, you can be sure that your electrical work is done properly and that your electrical system is safe and reliable. This provides some context on the potential consequences of improper electrical work. Improper electrical work can have serious consequences, including electrical shock, fire, and property damage. Electrical shock can occur when someone comes into contact with a live wire or a faulty appliance. Electrical shock can cause burns, muscle spasms, cardiac arrest, and even death. Fires can occur when electrical wiring overheats due to overloaded circuits, loose connections, or damaged insulation. Electrical fires can spread quickly and cause extensive damage to property. Improper electrical work can also lead to property damage. For example, improperly wired receptacles can damage appliances and electronic equipment. In addition, improperly grounded electrical systems can cause corrosion and damage to metal pipes and structures. The consequences of improper electrical work can be devastating. That's why it's so important to hire a qualified electrician to perform all electrical work. A qualified electrician has the knowledge, skills, and tools to ensure that electrical work is done safely and correctly. By hiring a qualified electrician, you can protect yourself, your family, and your property from the dangers of improper electrical work. Now let's dive into some real-world examples of electrical hazards and how to prevent them. Real-world examples of electrical hazards are numerous and can occur in various settings. Firstly, consider damaged extension cords. Frayed or cracked extension cords can expose live wires, creating a shock hazard. Prevent this by regularly inspecting extension cords and replacing them if damaged. Secondly, overloaded circuits. Plugging too many devices into a single circuit can cause the wires to overheat, leading to a fire. Prevent this by using power strips with surge protectors and avoiding overloading circuits. Thirdly, wet locations and electricity. Water is a conductor of electricity, so using electrical devices in wet locations can be extremely dangerous. Prevent this by using GFCIs in bathrooms, kitchens, and outdoor areas. Fourthly, improper use of appliances. Using appliances that are not properly grounded or that have damaged cords can create a shock hazard. Prevent this by ensuring that all appliances are properly grounded and that cords are in good condition. Fifthly, working on live circuits. Working on live electrical circuits can be fatal. Prevent this by always turning off the power to the circuit before working on any electrical components. Sixthly, contact with overhead power lines. Contact with overhead power lines can cause severe electrical shock or death. Prevent this by being aware of overhead power lines and maintaining a safe distance from them. Seventhly, amateur electrical work. DIY electrical work without proper knowledge and experience can be dangerous and can lead to serious electrical hazards. Prevent this by hiring a qualified electrician for all electrical work. Eighthly, neglecting electrical maintenance. Failing to maintain electrical systems can lead to various hazards over time. Prevent this by scheduling regular electrical inspections and maintenance. Ninthly, using incorrect bulbs or fuses. Using bulbs or fuses with incorrect wattage or amperage can overload circuits and cause fires. Prevent this by using the correct bulbs and fuses for each fixture or circuit. Tenthly, tampering with electrical meters. Tampering with electrical meters is illegal and can be extremely dangerous. Prevent this by never attempting to tamper with electrical meters. By understanding these real-world examples of electrical hazards and taking steps to prevent them, you can create a safer environment for yourself and others.